Welcome back to another lesson. Today is a good day. It's Friday, and we have a new lesson, and it's related to what we've been doing. It's just a slightly different analysis piece that we have to add in here. So what we're looking at is called the discriminant and the nature of roots of quadratic functions or quadratic equations. All right, so we're going to be using some words today like rational numbers, irrational numbers, real numbers, complex numbers, imaginary numbers. So I want you to see what the complete number system looks like. So all throughout middle school, Algebra 1, Algebra 2, your life has been here, inside of the real numbers, okay? By adding imaginary numbers, which I did in a couple previous lessons, you learned what the number I is. Okay, it stands for the square root of -1. So this is our whole number system, and it's called the complex number system. All right, real numbers can be written in the form a plus bi, where b is 0. So a real number, for example, could be 5, but we could write this as a complex number by saying 5 plus 0i. This number right here belongs inside of the real numbers, okay? We just don't write our numbers this way. So all numbers are considered complex, and the one gripe that I have with this image is the fact that they split imaginary numbers into two. There's really just one circle here. This wasn't my image, so I couldn't edit it, but there's really just pure imaginary numbers, numbers that can be written in just bi. That's what belongs in this circle. All right, but this is our number system. These are numbers that go on number lines. So these are numbers that we can put on the XY plane. Numbers that deal with complex numbers that deal with imaginary numbers do not go on the XY axis. Okay, and that's going to become important when we go to sketching quadratic functions. All right, so I just wanted you to see the number system and how it's laid out. So just to quickly go through the real number system. Okay, the real number system contains all numbers that fit on a number line. Okay, so within the real numbers you have kind of two sets. You have irrational numbers. These are numbers that are non-repeating, non-terminating decimals. And then you have rational numbers, which can be decimals, but they're decimals that repeat or terminate. Okay, so decimals that repeat, for example, like 1/3 is 0.3 repeating. That is a rational number. 1.25, that is a terminating decimal and can be represented by a fraction. So an alternate definition for rational functions is a number that can be represented by a fraction. All right? Irrational numbers cannot. So numbers like square root of 2, pi. There's a number called e, which you'll learn about later this year. 5 plus square root 2. That number, if we were to get the decimal, that is an irrational. So you've seen irrational solutions already in previous lessons. Okay? So inside of rationals, you can break down rationals into integers. So those are positive and negative whole numbers. Then you have just whole numbers. Those are positive counting numbers, including 0. And then we have the natural numbers, which are all the numbers starting at 1 and going up 1, 2, 3, 4, so on and so forth. All right, but this is our number system. I wanted you to see this graphic so you can kind of understand when I say the roots are irrational, where that lives in our number system. All right, this next graphic is pretty much the same picture as above, but these are all the symbols that are used for each number set. So we've talked about the real numbers this year, and the symbol that's used for the real numbers, well, there's a symbol for rational, a symbol for integers, a symbol for the natural numbers, a symbol for complex numbers, and a symbol for imaginary. You're going to notice that there's a couple sets missing from the graphic above this, but we don't really use a symbol for irrational numbers. If you Google it, you might see a P, a fancy P, okay? And you don't see a symbol for whole numbers. It just depends on the author of whatever book you're following, Okay, but I just wanted to show you these. If you ever run across these at some point in math, at least you've seen them somewhere. Okay, so we have seen through previous lessons that the solutions, which are also called roots or zeros, of a quadratic can either be real roots or real solutions or complex roots. Okay, we saw that in the lesson from yesterday with the quadratic formula. Okay, now under real roots, there's kind of two subsets of the real roots. We can either get rational roots or irrational roots. Now, after doing a couple problems with the quadratic formula, you're going to like rational roots because those are the ones that have a perfect square underneath the square root. Okay, irrational roots are the ones that do not have a perfect square under the square root. So, these are the type of roots that you're going to get from a quadratic equation. All right, now, the value of the discriminant. That's the topic of today's lesson. The value of the discriminant will represent by a capital D is equal to b squared minus 4ac. Notice that's the part underneath the square root in the quadratic formula. Okay, what this does is it tells us how many and what type of x-intercepts, or zeros or roots or solution, which are also known as the nature of the roots a quadratic function or equation may have. So there's three different cases when we're dealing with the discriminant and how it relates to the nature of the roots. So the first one is going to be where the discriminant, b squared minus 4ac, is a positive number, is greater than 0. If the discriminant is greater than 0, the quadratic equation or function is going to have two real roots. So that is two real number roots. All right, so what is that going to look like on a graph, or what could that possibly look like on a graph? Well, we're dealing with the quadratic, and quadratics are parabolas, as we mentioned in previous lessons. So one possibility is that your graph looks something like this, where it hits the x-axis in two places. That's what creates the two real roots. Remember, real numbers are the only things that show up on the xy plane. Okay, well, it doesn't have to look like that. Another option is that the graph faces down, and it might look like this. All right, so that is also a possibility for the graphs. And we're going to look at plenty of graphs, so don't worry. The main thing I want you to take from this is just that the graph hits the x-axis twice. Okay? So the second possibility is that your discriminant is equal to 0. All right, so the first one is greater than 0. The second one is equal to 0. So in this case, you're going to have one real root. Now, when you're solving equations, this number might be repeated twice. Okay? If you remember back to solving equations by factoring, a couple of the equations resulted in the same number repeated because you had two of the same factors. Okay? That's what we call one real root. Okay? And what this looks like on a graph here is just one example. I'm just going to give one example. It means that our graph is only going to hit the x-axis at one point. So what this means is that our graph's vertex has to lie on the x-axis. So here's an example of a function whose discriminant would be equal to 0. All right. The last case is if b squared minus 4ac, the discriminant, is less than 0. So if it's less than 0, we're going to have two complex roots. Okay, so what does that mean on a graph? Well, if the roots are complex, that means that they're not going to show up on our xy plane. So what's going to happen with the graph? Well, our graph might look like this, where it doesn't touch the x-axis, or it might be facing down over here and not touch the x-axis. But the key thing is that maybe we should add this under each box. Okay. We can talk about the roots. Okay, but if we're referring to x-intercepts, that's, even though it's the same word, on a graph it kind of looks different. So if we have two real roots, that means two x-intercepts. If there's one real root, that means one x-intercept. Okay, and I abbreviated intercept there. You can do the same. And finally, if there's two complex roots, there's no x-intercepts. Okay, so you can have complex roots or complex solutions, but if it's in the context of asking for x-intercepts, we say there is no x-intercepts. So we're going to take a look at example 1. It asks to find the discriminant and describe the nature of the roots. All right, so we have, let me move the mouse. A equals 5, B equals -4, and C equals -1. So our discriminant is b squared minus 4 times a, which is 5, times c, which is -1. Now I got to simplify that. So I have 16 minus 4 times 5 is 20, times -1 is -20, but I have a minus, so minus and -20 is going to be plus 20. It's equal to 36. So according to our chart that we just filled out, this discriminant is greater than 0. Okay, I'm abbreviating discriminant. Since the discriminant is greater than 0, there will be two real roots. Okay, the discriminant doesn't tell us what the roots are. If we wanted to find the roots, we'd either have to use factoring or the quadratic formula, but it just tells us about what type of numbers they're going to be. That's what the discriminant does for us. Okay? So, a second example. We have a quadratic equation here, which we can still use the discriminant to talk about the solutions to this equation. Before we use the discriminant, though, it has to be in standard form. So we have to have one side set equal to 0. Okay, so rewriting this equation, I would have x squared plus 3x minus 9 equals 0. So a is 1, b is 3, c is -9. Now, the discriminant, I guess I should write capital D to notate what I'm actually finding. The discriminant is equal to b squared, so 3 squared, minus 4 times a, which is 1, times c, which is -9. Okay, which is equal to 9. 4 times 1 is 4, times -9 is 36. Sorry, I'm getting ahead of myself. 9 plus 36 is 45. So again, 45 tells us that there's going to be 2 real roots. Okay, I wrote a little longer sentence on the first one because this is your notes. I wanted you to know why there's 2 real roots. This one follows the same pattern, so I'm just putting 2 real roots. That is a description of the nature of the root. All right, so example 2, we're still using the discriminant to describe the type of x-intercepts this time. All right, so we're no longer just describing the roots. Okay, I want to know about the x-intercepts. So I'm more talking about the graph. What is it going to look like on the graph? So I have this function, it's called g of x, where a is 2, b is negative 12, and c is 18. Okay, and I need to figure out what the x-intercepts of this function are going to be. So, taking the discriminant is negative 12 squared minus 4 times a times c. All right, so doing the math here, I got 144. And I have 2 times 18 is 36 times 4. I didn't do this beforehand. It's also 144. And 144 minus 144 is 0. So, according to our chart up here, if the discriminant is 0, then it's going to have 1 real root, which, according to our graph, is going to have 1 x-intercept. Okay? So, since capital D is equal to 0, since the discriminant is 0, there is 1 real root, which means 1 x-intercept. All right, so second example, same set of directions. We're asked to find the number of x-intercepts or describe the x-intercepts. So, looking for the discriminant of this function, we have a is negative 5, b is 8, c is negative 9. Okay, the discriminant would be 8 squared minus 4 times negative 5 times negative 9. So 8 squared is 64 minus 4 times negative 5 is negative 20. Negative 20 times negative 9 is 180. Okay, and 64 minus 180 is negative 116. And according to our chart, we know that when the discriminant is negative, there's going to be 2 complex roots. So what does that tell us about the number of x-intercepts? Well, again, I mentioned that complex numbers don't belong in the xy axis. Okay? That is only for real numbers. So what this tells us is that 2 complex roots means no x-intercepts. Okay, so next example, we get away from just kind of the plain, take the discriminant, use the chart to describe the nature of the roots, to something that's slightly more interesting, okay? So, find the values of k, value or values of k, such that this function, x squared minus 6x plus k, has 2 complex roots. Okay? So, two complex roots, this is kind of the thought process here, tells us that the discriminant has to be less than 0. All right, so using that fact, the discriminant is equal to -6 squared, that's b squared, minus 4 times 1 times k. Okay, I'm just plugging in what a, b, and c would be. C would be a constant, I know or c would be k, which I know is a variable, but you'll see in a second what we're going to do with that to figure out what values k can take. All right, so doing a little bit of simplifying, we would have 36 minus 4k. So this is the discriminant in terms of k. So we have up here that the discriminant has to be less than 0, so that means 36 minus 4k has to be less than 0. All right, so we can solve for k here. It's just a inequality, so we have subtracting 36 from both sides leaves us with -4k less than -36. Divide by -4, which dividing by a negative flips the inequality, and we have to get that k has to be greater than 9. So any value for k that is greater than 9 is going to produce a function that has two complex roots. Last example, it says find the values or values of b such that y equals 2x squared plus bx plus 8 has one real root. So think, what will tell us if the function has one real root? Well, that's if the discriminant is equal to 0. If the discriminant is equal to 0, then there is one real root. All right, so I need to see what the discriminant is. In this case, the discriminant is equal to b squared minus 4 times a times c, which, simplifying a bit, I get b squared minus 64. So that's the discriminant in terms of b, and b is our unknown because that's what the question's asking for, the values of b. So we know that this discriminant has to equal 0 if there's going to be one real root. So we have b squared minus 64 equals 0. Well, look here. This is a quadratic equation. It's a quadratic equation that we've previously seen. Okay, we're going to solve this using factoring. This is what's called a difference of squares. So to factor a difference of squares, the square root of your first term goes in both sets of parentheses. So the square root of b squared is b. One factor is going to be plus, the other factor minus. Then the square root of the second term is going to go in both sets of parentheses. So the square root of 64 is 8. So it goes there. Now this is equal to 0. So this is the factored form of b squared minus 64. Now you use the zero product property to set each factor equal to 0. And then solve for b. So b has to equal -8, or b can equal 8. Both of those b values will produce a function that only has one real root. So that's the end of the lesson. The discriminant, all it does is tell us what's called the nature of the roots. Okay? So, hope this video helps, and I'll talk to you soon.